Normal and shear stresses on a plane. So students in a soil mechanics course are familiar with the fundamental principles of the mechanics of deformable solids. So this section is a brief review of the basic concepts of the normal and the shear stress on a plane that can be found in any course on the mechanics of materials. So we have here a figure. So this is a two-dimensional soil element that is subjected to normal and shear stress. So a soil element, and there are two kinds of stresses acting on it. One is the normal stress, designated as sigma, and the other one is a shear stress, designated as tau. Taus of n, sigmas of n. So we know that from the mechanics of deformable bodies, normal stresses, when we say normal stresses, these are stresses acting perpendicular to the reference plane. When we say shear stresses, these are stresses acting parallel on a side or on a reference plane. So from there, we have here normal stress acting perpendicular on plane CD. By the way, this is our soil element, two-dimensional, point A, point B, point C, and point D. And then we also have a plane at a certain angle, and that is point E and point F. So this is plane EF. And it has a certain degree of angle with reference to plane AB. Plane AB. So going back, we have here a normal force, normal stress acting perpendicularly towards this plane. So this is your normal stress along Y direction. So if we have a normal stress on the Y direction, we also have a normal stress acting on X direction. Then next is the shear stress. So we have here your shear stress acting parallel or on the side. So this is designated as shear stress crossing the y-axis acting along x direction. So shear stress crossing the y direction acting along the x-axis. We also have here your shear stress crossing the x-axis acting along y direction. So T or taus xy. Principle of equilibrium would say that if we have a force going down, there has to be a force also going up. So this is also your normal stress along y direction. Along x direction, we also have to have here your normal stress along x direction. Why? Principle of equilibrium. Same with our shear stresses. So if the direction of our shear stress is towards this direction, from here, our direction is towards the opposite side. So this is taus of yx or shear yx. And then if this is going down, this is going up. So next is to consider this free body diagram. So this figure you see here is this part. We just transfer it out for us to be able to analyze it. So this is plane E. This is B. This is F. So this is your plane EF. And then, let's also copy the forces acting on it. We have here your normal stress along y direction. We also have your normal stress along x direction. And then, we also have the shear stress. Shear stress crossing y-axis acting on x direction. Then we have here your shear stress crossing the x-axis acting on y direction. So, from this free body diagram, we know that there is also a force acting along plane EF. So for us to get the forces acting along the plane EF, we simply have to apply the principle of equilibrium. So the normal stress acting perpendicularly. So since it is compression, this is also compression. This is now your normal stress along n direction. And then we know also that there is a shear stress acting on the side of the plane or parallel to the plane. So we have here your shear stress. Now, what will be the direction of your shear stress? Is it towards this direction or towards this direction? So from here, we know that our theta is referenced on horizontal plane or plane EB. So this now becomes our reference plane. So the shear stress on plane EB is clockwise. Therefore, the direction of our shear stress here should be counterclockwise. Principle of equilibrium. So this now becomes our shear stress. So in geotechnical engineering, this is now the concern. This is now our concern, the normal stress and the shear stress. The normal stress and the shear stress. From the principles of mechanics, engineering mechanics, if we get the summation of forces along n direction, of course, for the forces here, remember we have a normal stress acting along y and along x. We also have a shear stresses acting along yx and along xy. So if we get summation of forces along the n direction, we have to get the component. So, say for example, this normal stress will have its component, Txy, or shear stress along Yx will have its component. Normal stress along X and the shear stress will have their own components. And then if you get the components of each forces, you can now get the summation of forces along N. Then from there, we can derive the equation for normal stress. Okay? So, summation of forces along N to derive the equation for normal stress. And then summation of forces along, this is supposed to be T. Sorry, okay? Summation of forces along T for us to derive the equation of shear stress. So from the derivation, we now come up with the equation for normal stress, that is sigma y plus sigma x divided by 2 plus sigma y minus sigma x divided by 2 cosine 2 theta plus taus of xy sine of 2 theta. We also came up with the derived equation for shear stress, that is sigma y minus sigma x divided by 2 multiplied by sine 2 theta minus shear xy cosine 2 theta. So we have here soil element, and every orientation of the plane will get different stresses. So there are thousands, if not hundreds, of planes, and every plane has its own shear stress and normal stress. So if the plane is parallel, so this plane will get the same value of shear stress and normal stress as this one. But if you have different angles, the orientation or different orientation, you will get different values for shear stress and normal stress. Now, there is an orientation of a plane that has no shear stress. If we substitute 0 for shear stress, we come up with tangent to theta is equal to 2 shear stress along xy divided by normal stress along y direction minus normal stress along x direction. When you know the value of your shear stress, you know the value of your normal stress along y, and you know the value of your normal stress along x direction, you will come up with two values of theta. There will be two values of theta which are 90 degrees apart. So the plane where there is a zero value for shear stress, we call that a principal plane. Of course, on the principal plane, there's still a normal stress acting on it. So the normal stress acting on the principal plane is called the principal stress. So you have here your horizontal plane, that is your angle. This is now your principal plane, wherein there is a zero value for shear stress. And then the normal stress acting on this principal plane are called the principal stresses. So there are two, the major principal stress designated as sigma 1, and then the minor principal stress designated as sigma 3. The principal stresses are computed using the following equations. So note that the major principal stress is designated as sigma 1 and the minor principal stress is designated as sigma 3. Basically, the equations for sigma 1 and sigma 3 are the same. The only difference is that this operation, so if it is sigma 1 or if it is a major principal stress, this is positive, and if it is a minor or the sigma 3, this is negative.